This is Professor Coles. We're going to go through a hydrostatic problem. In this case, we have a box floating in the water, and what we're going to do is figure out what the forces on the box are due to the pressure in the water. We assume that the box is stationary and that the water is still. Pressure distribution on this box is going to look something like this. We have on the top an atmospheric pressure pushing down at 101,325 pascals. That's the standard pressure of the atmosphere at sea level. We have pressure of the atmosphere pushing here, and then once we get in the water, the pressure is increasing appreciative amount. I should have started it at 1 atmosphere. It starts at this 1 atmosphere, and then it will continue to increase as we go down into the water column. The same on the other side. We have the atmospheric pressure, which also has a hydrostatic component to it. The pressure in the atmosphere is greater the lower you go, or in the contrary, it lessens as you go higher. But over this kind of distance, it's a negligible amount. So we consider constant atmospheric pressure. The pressure right at the water surface is atmospheric as well. It must match the air. And then it begins to increase as we go down. On the bottom, we have constant pressure, because again, the pressure is given by, at any point here, for example, a point right here, is that the pressure here is rho g h plus pa, where pa is the atmospheric pressure, right here, and this right here is the dimension h. Rho gh plus pa, right here, the bottom. Now by symmetry, we can argue that the net force due to pressure from the left and the right of the box, from this side, is equal and opposite to this side. So there's no acceleration of the box in the horizontal, which intuition should tell us is the case. So we're left with a force balance in the vertical. We have pushing down this set of pressures and pushing up this set of pressures. This set of pressures and pushing up. The pressure is a normal force, so the act of the pressure pushing on this side cannot produce a force in the vertical direction, because this side faces left and doesn't have any upwards or downwards components. So we have pressure of the atmosphere on the top, and on the bottom we have pressure of the atmosphere plus rho g capital H, where capital H is this dimension that's sort of hidden right here, which is the depth, the submerged depth of the box, the distance from the water line to the bottom of the box. Pa on the top pushing down, and Pa plus rho gh at the bottom. The net force due to pressure is up, so this is the z coordinate. I'm doing a sum of the forces in the z direction. The sum of the forces in the z direction are going to equal the pressure on the bottom of the box. This is an L by L floating box, so we're going to have equals Pa plus rho gh times L squared times the surface area of the box, minus, pushing down, Pa times L squared. And the other force we have in here is the weight of the box itself, minus HL squared, minus, we'll just say mg. Where m is the mass of this box, and g is the gravitational acceleration. So we have pressure forces and we have weight. So weight is a gravitational force acting on every molecule in that box. The pressure forces act on the surface of the box. We can see the atmospheric pressure disappears, and we're left with this basic equilibrium that mg is equal to rho g h L squared, which is equal to rho g times the submerged volume of the box, Vs, right here. HL squared is not the dimension of the box because some of it is above the water line. Rho GH square L squared is the submerged volume of the box. So we have weight equals rho g times the submerged volume of the box. And this is in fact Archimedes' principle, that the weight of the buoyant item, the weight of the floating item, is equal to the weight of the water displaced by that buoyant item. So we take this box was pushed into the water column, and it pushed a certain amount of water out of the way. That volume of water is equal to L squared times h, the submerged distance. That's the amount of water that's been moved aside for this box. The weight of that water that was moved aside is equal to the volume of that water times gravitational acceleration times the density of that water. Rho g L squared h, or rho g Vs as I called it, the submerged volume. And so that's Archimedes' principle, that this weight of an object is equal to the volume of the water displaced. Weight of the water displaced. So the weight of an object, of a floating object, is equals weight of weight of water displaced. In the simple case, where we have constant density, it's just simply equal to rho of the density of the water that it displaced times gravitational acceleration times the volume of the water that was displaced. And that was, you can Google that, that goes back some time. And we essentially just saw that in this simple example, where we have this box, that you can derive that relation for this. If you have a more complicated example, something like this with, where the object is a more complicated shape, something like this, you can go through the same exercise and you will get the same result. And here it'll end up being an integral, that the weight of this body is equal to the integral, rho g, let's put rho inside, is equal to the integral over this volume right here of rho dv. So we integrate over the volume of rho dv. If rho is constant, we can pull this out and we just have an integral over dv, which is equal to the volume, rho gv, if rho is constant. Which for most things, like a boat, you can essentially assume to be true. So it doesn't matter what the shape is. So here, the underwater volume is the volume of this thing right here. The volume of that underwater portion, that's the amount of water that's moved out of the way or displaced, and the weight of that water is rho g times that volume of underwater portion. And that's equal to mg, the weight of the object, the gravitational pull on that object. And so again, you have this sort of pressure forces acting all over this body. They're higher at the bottom, less at the top with atmosphere. But the net effect of that pressure force is no acceleration left or right, into or out of the page, and a net vertical pressure force, which is only there to balance the weight of the object. So when we think about that, we can actually start to think about these simple flows that can be set up when you have horizontal pressure differentials. So if we take this case right here, and this is just a thought problem, nothing more, we have cold fresh water and we have warm fresh water. So the only difference between these is the temperature in terms of, if we think about density. And we'll ignore for this instant the effects of pressure on density. We'll consider these to be small, rather small objects, maybe a meter by a meter cube in front of the class. The colder water is the higher density. So the high densities on this side and the lowest densities on this side, and they're separated by this membrane, which we'll call a diaphragm, that runs down the middle here. So time t equals 0 separated by this membrane. And the question is, what happens just at the instant that the membrane is broken? Will this flow continue to stay like this? Is stable equilibrium with cold water on the left and warm water on the right? And we can think of this in terms, at the instant that membrane breaks, in terms of what's going on with the pressure field. In particular, think about what's happening at the bottom. Are the pressures on the bottom matching on either side of the membrane. Well, the hydrostatic pressure is rho GH. It is the same, let me use a little more contrasting color. It is the same on both sides. The difference is the density on both sides. So the density on this side, rho left, is greater than the density on this side. Therefore, the hydrostatic pressure on the left side is greater than it is on the right. And that means if you're a water parcel sitting just here, straddling this interface at the time that membrane is broken, that the pressure you feel on your left side, this side right here, is greater than the pressure on the right. And you will be pushed in this direction right here. And we'll see this sort of cartoony thing be a little clearer. We'll be using this in the later part of the semester when we look at baroclinic pressure gradients. This is sort of an extreme version of that, but we'll be looking at the idea of what happens if you create a side-to-side pressure difference due to a density field. In this case, we're looking at temperature differences. If we come to this case below here, we have warm fresh water and overlying cold fresh water. So the same water masses, the same two water masses, but we just turn the box sideways. But we have gravity acting down. So gravity tends to produce an asymmetry to the situation. This rotation produces a different dynamic. In this case, do I have any side-to-side pressure differential? So the pressure here is equal to the pressure here. The pressure here is equal to the pressure here. So my pressure gradient is only vertical in this sense. I have just increasing pressure. So the pressure as I go through the warm, fresh water, the pressure is going to be increasing. So the pressure, let's say it starts at 0 at the free surface, increasing hydrostatic pressure, and then I get to this interface here, and this is colder fresh water, so the density is a little higher, and so I'm going to have increasing pressure from here, a slightly different slope. And so it's a stable fluid, the pressure is only increasing, and warm fresh water will reside over the cold fresh water, provided no one bumps this. If it just sits there, the only thing that will change is over a while, once we break the diaphragm, there'll be some very slight mixing, very slow mixing between these two fluids. But aside from that sort of Fickian or Brownian mixing, there will be no alteration of the situation. If we take the opposite of that, put the heavier fluid on top of the light, now we have a situation where we have an unstable situation. The density here, rho here, is greater than the density here. And so a fluid parcel right here weighs more than a fluid parcel of the same volume right here. And so what they want to do is exchange, and they will in fact exchange very rapidly. We'll have overturning will occur, and the system will right itself, like a ship righting itself, such that the cold water is underneath the warm fresh water. In the process of righting itself, you can have rapid mixing that occurs, and that rapid mixing will mean that we no longer have two distinctive fluids in this container. The last case, so this is an unstable case. This is a stable stratified case. And this last case right here that we want to look at, we have cold fresh water and warm salty water. And what's the deal with this? Well, we have to think, what are the densities that we're dealing with? How does the top density compare with the bottom density? Now it's colder, and this is warmer, so that implies the temperature contribution would produce an unstable situation where the upper parcel was of a higher density. But the bottom is saltier than the top, which has the opposite effect. So unless we knew the actual values, we couldn't say whether or not this was an unstable situation, possibly a neutral situation, if they were happen to be the exact same densities. So this is, you don't know without the numbers. So we have these four kind of scenarios to think about. The only thing we have is varying density, depending upon whether or not the pressure gradient's aligned or is orthogonal to gravity. We have very different flow fields that are created, and we'll think about these when we go out through the semester. In this case, in these three cases that we have here, try to erase some of the stuff, the isopycnal, which is the lines of constant density, are horizontal. This interface in particular between them is horizontal. It is orthogonal to gravity, is at right angle to gravity. This, in this case over here, the isopycnal, or the lines of constant density, is parallel to gravity. This would be an extreme case in the ocean, which wouldn't necessarily occur. We will look at cases where we have density an interface between two fluids that's sort of in an angle like that, and we'll consider the implications of that as being between these two cases, the left and the right cases. This is between these two, and we'll consider the implications of that as the semester goes on.